colleague now, former colleague Alex Belton, former student Natchik, postdoc. Yes. So the plan of my talk is it's in two parts. The second part, the main part, the first part, and some analogy in the Mary's talk moves from part one to part two using temperature, non-trivial variances. So I begin with the setup and spend a few slides talking about the relationship between Fock space and Venus space. Then explain the notion of stochastic cocycles in this time with a bit of quantum algebra, and with that talk about the generation of stochastic cocycles. There's a little bit of connection there with parts of Madeline's talk, Madeline Guter's talk. And then I'll go to discrete time, so I'll give the continuous time first, the discrete time, and describe the first main theorem here, which is a functional central limit theorem in a quantum context, Donsker type theorem, which involves embedding and scaling discrete time cocycles, in fact, which you may call quantum random walks. Then, in order to illustrate with an example, I will describe a very interesting transform due to Polevo. And in the second part, I will use quasi-free states and look at this process in a context of fateful states in so-called particle algebra, part of the essential ingredients of the whole setup. So, a quick review of the properties of the notation using that are needed here. So, here we're talking about bosonic Fock space over a Hilbert space, and in such a setting, contractions on the Hilbert space extend to contractions on the symmetric Fock space, and we have these particular vectors, exponential vectors, which play a very useful role in theory, and all exponential vectors with satisfy this exponential relation. And the normalized exponential vectors are useful for us as well. So it's far high for the normalized exponential vectors. So their end product is given by that formula there. The exponential property of Fock space is that if you take the symmetric Fock space of a direct sum, then that's naturally the tensor product of the Fock spaces. So it's the unsymmetrized tensor product. And thereby the Fock space over a subspace embeds into the Fock space over the full space in a simple way to the level of vectors and similarly at the level of operators. We have the Fock-Weil operators. These are the exponentials of P's and Q's. And in terms of the normalized exponential vectors, translate the argument with the phase factor and apply to the map. This simply gives a normalized exponential vector. Satisfy the canonical commutation relations in exponential form or Weil form. Revisit. Okay. So Fock on the one side and Wiener on the other side. So by Wiener space, I mean Venus, the space of Venus probability measure on continuous paths starting at 0 on the positive half line. And that is called BT canonical Brownian motion. And that in the setup is just defined at omega, its evaluation of omega at t. So with in this setting, we have filtrations, the filtration of the Brownian motion, the intrinsic filtration. Have this sort of doubly indexed version of the filtration. So in this talk, single index and double index, and moving between the two will be quite a theme. And if we consider in the process of moving from classical to quantum, consider the Brownian motion time t as a multiplication operator on the Venus space, for that qt, quantum point of view, pt, other Brownian motions, and we shall see such things. Very useful device here is quantum Wiener integrals. These are stochastic integrals where what you're integrating is actually an ordinary non-random function. So they're the simplest kinds of stochastic. And this is the basic definition of them for an indicator function of a box in the n simplex over the positive half line. So Bn is less than or equal to n plus 1 for each n. So the integral of that, the Wiener integral of that, is just the product of the Brownian increments. That extends linearly, and it's very easy to see from the properties of Brownian motion, independence of increments, and so on, that first of all, for linear combinations of these, the quantum Wiener integral of the function f of the simplex is normal mean zero and variance norm f squared, and that extends them to all symmetrical functions. So with that, one thing that can be done is to take this function of the n equals 1 level, integrate that exponentially to square root of -1. Then we have a family indexed by f, and then by elementary properties of Brownian motion. This family has this property here. We have two of them. This works out as this quantity here. So sorry, just have to do that calculation. So now we can take Fox space over. So our H is going to be square integrable functions on the positive half line with values in a multiplicity space, which could be C, one-dimensional. That's set up here. And because of the exponential property of Fox space, well, we have for every r less than s less than t, we have this direct sum decomposition of the spaces. So exponentiating that, we get tensor decomposition of corresponding Fox spaces. And again, we can embed a Fox space, let me say Fox space over RT, integral RT into the another Fox space here in a simple way. We can do it at the level of vectors and at the level of operators. If we do that, then we get filtration of Hilbert subspaces. 2 index, 1 index, and similarly filtration of subalgebras. So these filtrations of subalgebras are going to be appear as the natural notion of adaptedness to a filtration of subalgebras, which mirrors the classical probabilistic idea. What else do we have? Well, we have conditional expectations here onto these subalgebras. Conditional expectation with respect to the vacuum state. We have shifts, time shifts, sigma. And we also have time reversal on the interval 0 to t. So these are defined in very natural ways, second quantized ways, effectively. So this is all part of the structure we have. Some basic properties. Well, shifting subalgebra up to time t by s precisely gives you subalgebra from s to t plus s. Secondly, the family of conditional expectations has this tower property. It has this sort of covariance relation with a shift here. If you shift by r and then condition times 0, condition at time r, sorry, then that's equivalent to conditioning at time. So we'll see these algebraic relations in play, and this module property that so this is how it handles the non-commutativity here. Time R conditional expectation of something which is already in the time R algebra times the general operator times something else which is in the general time R algebra. The time algebra operators come outside in this last bit. So, 2 ways of thinking about how Fock space and Venus space are related. So we're going to start with a second. These multiple Wiener integrals here. You take an n-particle function here in the Fock space, making that correspond to the multiple Wiener integral of that function. That delivers, in general, for general n, the nth homogeneous chaos in the language of Wiener. That was Wiener's perspective on this. The Siegel's perspective, which is a little different. Alternative isomorphism is using those algebraic relations I mentioned earlier, simply mapping the normalized exponential vector of a pure imaginary function to this random variable here. And that's the relation which shows that this is it almost shows it's a unitary relation. The exponentials are spanning. The closed linear span is all of Fock space. The closed linear span of these particular random variables is all of Wiener space. So that's a description of the isomorphism between these two. I'm speaking about one dimensional Brownian motion. This generalizes to multiple dimensions very satisfactorily. So K will be the multiplicity space of the noise, which will become quantum soon. Right on Q. Remind you, Q of T was multiplication by Brownian motion of time T on Wiener space, but we now have an isomorphism across the Fock space. And there we have these first slide for any contraction on the space. There's an induced contraction on the Fock space, gamma C. If we find we take C to be square root of 1 times the identity, and you conjugate QT, get another Brownian motion. So the probabilistic properties are preserved. And the interesting feature here is, as with P and Q, normally these two classical stochastic processes are non-commuting. So what we do is we embrace that non-commutativity and take the whole together. Part of what I showed you. Next few slides. So by quantum stochastic cocycle, unitary, say, we have a family of unitary operators. They're indexed by the half line, starting at the identity. And instead of the group law is perturbed in this way. So at R plus T, we have not VR VT, but VR times VT shifted by R. And the last condition is that at time T, VT is living in the algebra up to time T. So it's adapted in the analogous sense to adaptiveness in classical problems. Given such an object, so there is a natural notion of continuity here. The notion is strong continuity as for unitary groups. Such a cocycle, if you condition out the noise, average out the noise, take the vacuum expectation, then you get a semigroup. The result of that is an actual semi. And that's follows by these relations we rehearsed in a few slides ago, properties of power properties conditionalized expectation, for example, modular property and so on. So you get a semigroup, the reduced semigroup, and elementary, well, it's just a convenient term for those cocycles whose expectation semigroup is non-continuous, so it has boundage in it. There is a dual semigroup to a dual cocycle to any quantum stochastic cocycle, and that's obtained by taking the adjoint and then doing this time reversal on the interval 0 to t. Now, each of those two operations separately would turn a left cocycle, which we're just discussing here, into a right cocycle. So combination of the two, so another left cocycle in the sense we're talking about here. And here is this cocycle to evolutions sort of traffic from a one parameter object, which happens to be a two parameter object, which is not shifting, and a two parameter object that is in the doubly indexed filtration of subalgebras in the algebra between, that should say, yes, between R and T. Okay. So some examples. Well, the trivial example is you take a unitary evolution and you just ampliate it, tensorize it with identity on Fock space. So that's the one in which there's no noise involved at all. Second example is, number one by numbering, is what you get if you randomize a unitary evolution. So you consider the group e to the I x, with x running over the whole line. Think of that as a spatial variable, and you replace x by Brownian motion. And then your unitary structure is replaced by its cocycle structure, reflecting symmetries of Brownian motion itself. So we can combine these two examples like this solution by considering the solution of this classical stochastic differential equation. In this classical equation, we have operators, so it's understood strongly. We apply it to to a vector. And that produces a cocycle, and there's no suggestion there's any commutativity between the Hamiltonian part and the distributive. Yeah. And then we can make a big jump and replace, and instead of having time and a single classical Brownian motion, P and Q, for example, put these together into a quantum Brownian motion. And actually there is a also what can be included is a Poisson process, number process. You can include this in one large gadget, and this will be a black box for the purposes of this talk. The other lectures to explain how you do it. So I'm going to talk about the, what you get. So solving a quantum analog of the stochastic differential equation of the type above yields cocycles. So the F here is what is replacing 2 by 2 block matrix, where you'd have IH minus a half A squared in the top left. You'd have IA top right, and minus IA bottom left. The further examples are pure noise examples you get from considering single vector in the multiplicity space C, and you take the Weil operator of the function, which is 0, takes the value C from 0 to T, and then takes the value 0 afterwards. So that gives you an example, because if you look at the product, the definition of cocycles, then shift by R on a Weil operator with test function C0 to T is just C on R to R plus T and 0 outside that. So that's that equation here. And now these two functions are orthogonal. So the product of the Weils is the Weil of the sum, which is so Weil of C 0 R plus T. So that's the verification of cocycle relation for this. So that's one kind of pure noise cocycle. And similarly, using second quantization of pure noise cocycle. So now a little bit of Ito algebra in a quantum setting. So Ito you should think of as in terms of Ito correction when you take functionals of Brownian motion. So how does this manifest itself in the quantum setting? A very simple algebraic structure. So we stick a hat on a Hilbert space K. We mean we're augmenting it by an extra dimension. And what we're doing is we're putting time and chance in one place. That means bounded operators on system space H tensor K hat can be viewed as block matrix operators, 2 by 2 block matrix operators, and that's the structure of such operators. Special projection here, 0, 0, 0, 1, and then we can view bounded operators on H tensor K hat as well, it has a semigroup structure with respect to the so-called series product. The series product is a perturbation of this addition of what will be generators for this. There'll be this is the ants which feature here. Input into this quantum differential equations to deliver this kind of process. So, so with this modification to addition, F1 and then sandwiching this projection here, F2, that reflects Ito correction in classical stochastic theory. Classical theory of stochastic processes. And we get a semigroup. The star structure is just the adjoint of operators. That's 0. So within that we have a star subgroup, and these are the ones which will generate unitary cocycles. So that's defined to be those for which F and series product with its star is 0. This family is very nicely indexed with 3 parameters. So in its block matrix form, we're after unitary cocycles, and the unitarity is first reflected in the bottom right component of the generator, namely that is some unitary minus the identity. L is an arbitrary column here. This is from H to H tensor A. The block in that top right is minus L star modified by this unitary. In some cases of interest, the unitary will be the identity, so that will disappear. And then the K is the dissipation coming from L minus half L star L, modified by a skew adjoint operator. So square root of 1 times a Hamiltonian, for instance. Okay, so the adjoint of that shows how the adjoint acts on its parameterization. And the second line here shows that what is going on here is a kind of modification of file relations, where you have, instead of simply test functions, you have operator value coefficients, would be a way of thinking about it. So here's culmination of many years' work and of simplifying the situation here. So this quantum stochastic differential equation, dxt is xt d lambda ft. So the ingredient is an operator of its block matrix shape. First of all, it has a unique solution, unique in an appropriate sense. The prescription, which takes F, we refer to as a generator, to its solution, that gives a bijection from this class U to the elementary unitary quantum stochastic cocycles. Top left of the block matrix operator F of K, then the expectation semigroup of the cocycle has generator K. Duality works nicely here. So the dual of the cocycle generated by F is the cocycle generated by the adjoint of F, which you see is still in the class. And lastly, how this series product is reflected in terms of the process is through a Trotter product relation, and that will have echoes in when I describe how you go from discrete to continuous. Okay. Fox space. So now that's the setup of continuous time cocycles. You can ask me afterwards what the some of the jokes are here. How many French, how many people whose mother tongue is French are here in the audience? Just. So Marius mentioned the necessity of having a reference family sequence of vectors when you take infinite tensor products. So here we're taking infinite tensor product as k hat c plus k. The reference vectors are 1, 0. I'm using this epsilon method for these toy Fock spaces. So we have echoes of all the structure I described in continuous time in discrete time. Filtrations, embeddings, so on. We also have conditional expectation in this setting. Especially toy vacuum, right? Time shift, time reversal. The structure is there at the discrete level. Now, much simpler than in the continuous time setting, we can embed B of H tensor K hat into B of H tensor the toy Fock space. Tensor copies, infinite tensor copies of K hat by simply taking T and mapping it to T tensor the identity after time 1. So it's just in the zeroth place. And the quantum random walk, or a discrete time cocycle, is just defined in the discrete analogous way to the continuous time object, starting at the identity at L time L plus N. It's the walk at time L times the shift by L, the walk at time N. And the walk is adapted to the filtration, to this discrete filtration.
So sorry, these are just what we call collision models in quantum information, aren't they? Yeah.
So that will be such things will be very nice examples of structure. Yeah, absolutely.
Examples, or are they exactly the same? Is this more general, or?
Well, that probably you have to tell me that. I'm not sure. Discuss that. So in this context, such an object is just generated by a single operator G. So the generator requires no analysis at all. Simply take a G, you embed it, do the toy embedding, shift, and then multiply the requisite number of times for the time. So very straightforward.
Can I ask one question?
Yeah,
So
sure.
if I start with semigroup or completely positive maps on B of little k, right? Finite dimensional matrix algebras.
Yeah.
Will this construction give me the cross operators for this e to the minus TL?
It will, both in I mean,
Discrete
you see that in a sense most easily in continuous time, but yes, it will.
You can do
Absolutely.
it.
So
You can also
so
do
the
it
L is Krauss, containing the Krauss information in the continuous time in the previous discussing before I went discrete.
So in some sense, this is just a very elaborate mathematical model for doing these type of calculations, right? I mean, calculating, I mean,
It gives a stochastic framework for dilation. So stochastic framework for dilation is a nice way to think about it.
You can write down stochastic differential equations satisfied by them.
Thanks. And duality works just as it does in continuous time. It's the definition of a dual, and the dual of the walk generated by G is the walk generator. So now what I want to do is embed discrete time walks into continuous time in order to show how limits work in this setting. It's very simple, pared down mathematical setting. So, first of all, we embed space which contains generators, both the walk generators and the stochastic generators, H, E of H tensor K hat, into E of H tensor Fock. By this formula here with respect to this isometry here. So very easy to see this is an isometry. And then we do what is a very natural thing here, discretize time. Here, and now we've got a continuous time process. So that is not going to be a cocycle itself, it's going to be an approximation to a cocycle. It will become a cocycle in the limit. So that's the formula. Take these products and notice it's a mirroring of how the walk is determined by the generator here. So let us refer to that as the H embedding of the quantum random walk generated by G. And then we need the right scaling matrix. So this is mirroring the functional central limit theorem scaling of one of the square root of H for the Brownian parts, 1 over H, the time part, and scale. Okay, so with that,
Well, you're
Yeah,
onto
sorry.
some kind of continuum limit now, or what is?
yes, exactly. We're going.
Sorry, yeah.
We're going to a continuum limit now. It's on the next slide. So that's first of all how we embed it, so we can ask the question, and then first theorem is that whenever you have a stochastic quantum stochastic cocycle F, and you have a family of walks whose generators, when writing them in this form, their block matrix, they have the property that taking off the identity, so G of H you should think of as an exponential IH of something. Of a total Hamilton. Then taking off the identity, scaling, and then you have convergence to your F in a certain sense. So the sense happens to be a hybrid between norm convergence and weak convergence. That's what it turns out to be the right one. And then you get convergence actually in the same sense, hybrid topology between norm and weak. We're mainly interested in the case where everything is unitary. If it is, then this delivers strong convergence, strong stuff of convergence of the adjoints as well. Some of the comments. And on the other hand, if the dimension of the noise is finite, really interesting, then this simplifies to operator convergence. So these embedded, scaled and embedded random walks converge to the cocycles. So cocycles are limits of such things. So two questions immediately arise. So given a generator of a cocycle, can you approximate? Can you find such GHs? Yes, you can. That's straightforward. One interesting question is, when does such a family converge to a cocycle? Second question. So a nice way to view, or very interesting cases when this does work, is through the transform goes back to Lego, trying to understand multiplicative stochastic processes. Something like that. So how does his transform work? Q goes to FQ. So Q is one of these block matrices. So it's defined in terms of a transform of a subtransform. So take 2 by 2 blocks. You put them into 3 by 3 blocks by putting them in the top right-hand corner, and then you have to switch the columns of the two, so it's the right shape, basically. So that's the tool map. And in terms of the tool map, the Halebo transform is apply the tool map, exponentiate, take off the identity, and undo the tool map. So a bijection. Okay, you can describe this in terms of skewer joint matrices. You can think of as the matrix you're exponentiating to get a unitary one-step generation of a random walk. In terms of the parameterization we gave for the stochastic generators by these three entire analytic functions. So explicit analytic formulae for how you get them. So as a consequence of the first theorem, we have, if you have a family of operators QH, skew joint operators, with the property that their scalings tend to Q, then the exponential of their scalings, so that's going to be unitary generator of a quantum random walk. Take off the identity scaling, that tends to the explicit stochastic generator FQ. So by theorem one, we have that whole class of convergence of random walks to cocycles. So that's a bit more detail on an example. I would like to spend the last part of the talk switching to how you modify, well, so spend some time.
We're trying to.
I'll be brief.
Very good, Martin, yeah.
Sure. Okay. How you modify this to take into account temperature? So quasi-free driven stochastic cocycles, how they arise. So here are the canonical commutation relations again. File form. We've been working in the Fock representation. For temperature, if you like. Quasi-free setting involves a conjugate copy of the Hilbert space H, underlying Hilbert space H, and covariance amplitude. Covariance amplitude has this shape here. The S is a non-negative operator on the Hilbert space. S bar just means it's conjugate version, and C is identity minus S squared square root, which gives us a quantum characteristic function, if you like, of this shape. So it's Gaussian, as you see, and case S is 0 is the Fock case, the degenerate case, if you like. If S is injective, then the vacuum here is still cyclic, and the Weil operators generate a type 3. So the message for the end of this talk is how GNS on the GNS construction representation associated with a faithful normal state on what I'm calling a particle algebra P delivers the structure of the previous slide. So it delivers a covariance for which you can consider its corresponding Brownian motion and ask that when do limits of quantum random walks in such a state, when they driven by quasi-free Brownian motions as opposed to top one is a kind of universal one within which you can fit such examples. So take the spectral resolution of the density matrix here, and now called K hat, the GNS space, which is the class of Hilbert-Schmidt operators on the particle algebra. And now I'm moving in the other direction. So taking off the one dimension generated by the square root of the density matrix, which is a Hilbert-Schmidt operator. Now take the linear span of the Dirac dyads of X and Y, where X is in the alpha eigenspace and Y is in the beta eigenspace. Take the direct sum of these things with alpha greater than beta, call that K, and the direct sum with alpha less than beta, call that K bar. This gives us a natural conjugate Hilbert space structure from K to K bar, namely the adjoint operation restricted to this subspace. This is Hilbert-Schmidt operators. So that's the conjugation. We have a decomposition of our GNS space there. We identify this first one-dimensional space with C, and we're back in a situation of C plus some Hilbert space. Now it's in two parts, K plus K bar, and a remainder part, which will play no role. So make that identification, and so our GNS space has that structure. Okay. So under an assumption on the decay of the eigenvectors, we can define a covariance amplitude in terms of state of this formula here. And then this will be injective. Interest. It's a technical slide which I'll miss. And here's the theorem in this setting. We take a total Hamiltonian of this type, and for our generator of a quantum random walk, we take the image under the GNS representation of e to the I h, total Hamiltonian h with total Hamiltonian of that type. And well, with that, things work out and we get convergence of embedded quantum random walks in this setting. And the cocycles that arise in this way are driven by quasi-free noises. So they're affiliated to the algebra generator of quasi-free noise. And the generator is explicit. And there are a couple of technical assumptions to make this works in considerable generality. Thank you for your attention and apologies to